interference via diffraction through one slit. I did post a video from it last night, and you can actually see some details that you guys couldn't see with the in-class because, well, the camera actually picked it up fairly nicely. You could see that there are, in fact, bright and dark spots. And then I took closer pictures. Yes, thank you. I took closer pictures with the phone, and those ones really show bright and dark locations, and I embedded them in the video. So if you look, you'll see that, yes, in fact, it's not just some long blob of brightness and then dark and then another long light. We talked in class about the pattern that you see with a single slit, which I've put a sort of picture of that right here for you all. Is usually you have a bright central fringe, and then it gets darker, and then it gets a little brighter and darker and brighter, and the centermost fringe is usually the brightest, and then it gets dimmer as you move away from there. And we talked about that. I showed you what the equation for it was. I talked a little bit about how to interpret the equation. So this is your equation. It tells you where the dark locations are. The dark locations would be like right here, right here. This one's a bright location. Okay, you may be wondering what the theta, where the theta comes into play. I'll draw a little diagram here that's sort of like an overhead view, if you will, of what's going on and where theta is located and all that. Because when you look at the screen, it's not really obvious how you get theta just from looking at a screen. You really just measure distances between one bright and the next, or one dark and the next. But what's happening is, from our overhead view, you have a slit, that's this little hole, that the light can make it through. And then somewhere farther away, you have the screen, like this. So this is your slit. This is your screen that you actually are looking at to see this pattern. And what happens is we define a location on the screen, which is straight across from where the slit is located. All right? And then we look out here on the screen at some particular location. Right there. This angle right here is your angle theta. So theta is basically describing what direction you have to go from the slit in order to find that location on the screen. Now this one is telling us where the dark spots are. How do you find the bright spots? Well, they're basically midway between two dark spots. If you wanted to measure this actual distance, we usually use like a delta y to represent it. You have to do a little bit of trigonometry. And basically what you do is, if you know how far this right here is, the length, from your slit to your screen, then delta y and this length are like the two legs of a perpendicular triangle. So now you have to think about trigonometric identities. So does everybody remember their trig identities? There's three that are sort of the most important ones. Sine, cosine, and tangent. These identities, when you have a right triangle, they relate the ratios of two of the sides and or the hypotenuse to each other. So it turns out that tangent of theta relates the length of the side that's opposite from the angle to the side that's adjacent to the angle. That basically means that tangent of theta gives you delta y divided by L. So if you're trying to figure out where on the screen is it, you measure the length and you look at what this angle is for, say, the first dark spot, and you rearrange this equation to get delta y is equal to L tangent theta. I don't think any of the homework problems go quite that in depth, though. I don't think you have to actually figure out where on the screen it is, other than maybe figuring out an angle. All right, what are the other terms in the equation? M, in this case, is what's called the order. It just is, it's like count how many dark fringes you've gone. So if I redraw this screen, and actually on the video that I posted, I did count for you one time with them. But in case you're not watching those or don't want to watch those or whatever, right here you're going to have a bright fringe. Maybe your next bright fringe is here, 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 etc. Okay, and then you'll have this mirrored below as well. So the order is looking at these dark fringes. This right here would be m equals 1. This right here would be m equals 2. This is m equals 3, etc. Now, how do you know where m equals 0 is? Because again, you also have these guys doing this below. So how do you know where m equals 1? Why is this one m equals 1 and not, say, this one? How do you know where to find m equals 1? The answer is, if you look back at the diffraction pattern that I made last time for you, or if you look on the video or at the pictures I took, or even at this picture here, you'll notice that there is one bright fringe which is brighter than all the others. That is this one right here. So this is the brightest bright fringe. So you count how many dark ones have you got away from that. That is your M. A, as a reminder, is how big the slit is. So this distance is A. How wide is your slit? With the thing that I brought to class last time, there were two options. You could have it be 0.04 millimeters or 0.08 millimeters. And then lambda is your wavelength. So how do you get the wavelength? Well, if you're using a laser for this, usually the wavelength is actually written somewhere on the laser. That's kind of a silly answer maybe, but it's a true answer. If you're using the lasers that I brought last time, the green one was 532 nanometers, the red one is 650 nanometers. Is there a better way of answering that question? Well, yes, but it's kind of complicated. There is a different way that you can measure it, though. I will tell you, though, one method you can use to measure, and you can do this at home, measure the wavelength of some sort of electromagnetic radiation, specifically microwave. You all, I think, have microwaves at home or in your dorm or wherever you happen to be, I assume. What you need is marshmallows. Preferably, you cover them so that they don't explode all over the inside of your microwave when you do this. But you can take a plate and just put a bunch, and miniature marshmallows work great for this. Just cover the plate with the miniature marshmallows, put it in the middle of the microwave, and let it run for 10 or 15 seconds, and then pull them out. And what you'll notice if you look at the plate is that there will be some marshmallows that are quite they'll be like burned even, but if not, they'll at least be toasted. And then there'll be some that are not cooked at all. They're practically raw. And then you'll see another one that's cooked, and another one that's raw, and another one that's cooked, and another one that's raw. And what you do is you measure the distance between two cooked marshmallows. And if you do that and double it, then you have the wavelength of the electromagnetic radiation from your microwave. All right. Now, for a laser, it's not very easy to do that way, because 500 nanometers, for example, or 600 nanometers is a really short distance to have to measure. 1,000 nanometers is a very small cell within your body, for example. So try to measure half of that. You can see where this would be not very practical. But you can do it some other ways. You have to build what's called an interferometer. Basically, what that involves doing is building a system in which you have a laser. And then somewhere in the system you have a device that splits the beam into two pieces. We call these beam splitters. Not a very imaginative name, but there you go. So this beam splitter maybe sends one this way and one this way. And what you do is you put a mirror here and you put a mirror here. So the beam hits the mirror, it bounces back, this beam hits the mirror, and it bounces back. And it turns out that these returning beams can come out down here, and you can put a screen. And sometimes what you get down here is a really bright spot. And sometimes what you get down here is a really dark spot, assuming that you've aligned everything correctly. So what determines whether it's a bright spot or a dark spot? Well, it turns out that what determines it is the difference in length between this and this. We call those the two arms of the interferometer. If the two arms are exactly the same length, you will get a dark spot down here. If you move this mirror by 1/2 of one wavelength, you'll get a dark spot down here. If you move it by 1 whole wavelength, you'll get a dark spot down here, etc. So any multiple of 1/2 lambda that you move one or the other mirror by, you go from dark to dark. What happens if you move by only 1/4 wavelength? If you move by only 1/4 of a wavelength, you get a bright spot down here. 3/4 of a wavelength, bright spot. 5/4 of a wavelength, a bright spot. Okay, now why is that? Why do you get bright spots or dark spots? Well, this plays into what's called interference, and it goes back to the thing we were talking about last time, or that I was talking about last time, where you can have two sources and they're both emitting a wave, and depending on how the two waves arrive, you either get a high point or a low point. Low point means dark spot, high point means bright spot. And there's one weird thing which happens, which is that one of these beams gets a little bit of added distance because it actually reflects an extra time off of this. And so that's like adding a 1/2 wavelength to the distance that it travels. So after you include that 1/2 wavelength, if both travel the same distance, or an integer multiple of wavelengths times the same distance, then they both arrive in phase. That means that peaks arrive together, troughs arrive together. Means the two peaks will add together to make a bigger peak, and so you get a bright spot here. If they arrive halfway out of phase, that's like having the peak from one and the trough from the other arrive at the same time. You add those two things together, they cancel out, you get a dark spot. And they will cancel out at all times. So it just stays dark. What this means is that if you can figure out how far you've moved one of these mirrors, then you can figure out what the wavelength is. So how do you figure out how far you move the mirror? Well, they make a special device called a micrometer screw, where you turn a screw and that causes the mirror to move this way or move this way, and a certain amount of turning gives you a certain translation distance. And so you can just turn it and see how far did you move the mirror, and basically maybe turn it through 1 millimeter and count how many times do you see dark and how many times do you see bright, and divide. And by doing that, you get the wavelength of the laser. So that's basically what the engineers who build the laser do in order to write the number on the back of it. It says this is 650 nanometers, or this is 632.8 nanometers, or what have you. All right. What about the double slit? So I demoed the double slit for you. I actually spent more time demoing the double slit than the single slit last time. But we never really talked about the double slit. It turns out that the double slit is actually in some ways easier than the single slit. In some ways. In some ways, maybe not. The reason why not is because each of these slits is itself a single slit, and therefore you have the single slit pattern present. But if you ignore the fact that each one has a diffraction pattern, and you just want to figure out the interference pattern, in other words, how far between this and this, as opposed to this and this, then the single slit's easier. Because the single slit is only two sources, not many sources. You'll recall that to discuss diffraction last time, we considered what would happen if you put people on a pool, like an inner tube in a pool, and the people jumped up and down on the inner tube like this, and then the next guy's got his inner tube and he's jumping up and down on it like this. Both of them make waves. Those waves interfere with each other. Well, two inner tubes actually does work for describing this. For describing the single slit with some width, you might have to have 50 inner tubes bouncing up and down. That's rather harder to figure out than two. So with two bouncing up and down, or with two slits, what kind of interference pattern do you get? Well, basically what you do is this. We draw our two holes. We put our screen here, and we ask, how much is the distance between, say, this hole and the screen at this point, and how far is it from this hole to the screen at this point? And we ask, what is the difference in length between those two things? What is the difference in length between those two things? You don't have to solve this. There's a bit of complicated geometry behind it. But you can figure it out for any point on the screen. And it turns out that for any point on the screen, it will follow a particular, roughly follow a particular pattern. You don't just ask, though, how far apart or how much is the difference between this and this. You have to ask also how many wavelengths worth of distance is there. So mathematically, that might look like this. We could call this L1, we could call this L2, we could say that delta L is defined as the distance between, or the difference between L1 and L2 that is passed through. And the thing that we care about is what's sometimes called like a phase angle. Delta phi, and that would be delta L divided by lambda times 2 pi. Why times 2 pi? Because you have 2 pi radians in a full circle. That's why the circumference is 2 pi times r, the radius. This is another way of saying times 360 degrees, if you prefer to think of it as that. All right, so delta L over lambda is the thing that we care most about, though. If delta L over lambda is equal to an integer number, 0, 1, 2, 3, anything like that, then you will get a bright fringe. It means the two waves will arrive in phase, like this. Both peaks arrive at the same point. If it is half of an integer, 1/2, 3/2, 5/2, etc., then you get this condition where you get a peak and a trough arriving at the same location. If you get a peak and a trough arriving at the same location, you get a dark spot. No light is there. All right? And it turns out that the pattern that tells us, is it going to be bright or is it going to be dark, is this. D times the sine of theta is in lambda for a bright spot. What is D? D is this distance right here. Lambda is your wavelength. Theta, again, I've drawn a dashed line that's perpendicular here and perpendicular there. Theta would represent the angle between that dashed line and the line that runs through the point of interest. So here is theta. So if D times the sine of theta is some integer n times lambda, the wavelength, then you will get a bright spot. If D times the sine of theta gives you a half integer, which we represent as n plus a half times lambda, the wavelength, you get a dark fringe. And that's how you figure out where are the dark and bright fringes. As with the diffraction pattern, if you want to measure actual distances along the screen, in other words, you want to know how far is this, once again, you measure what this length is from here to here, and you use the tangent of theta. And as with the diffraction pattern, where m represented the order, the same is true here. N is what we call the order. Now the difference is that with the diffraction pattern, m had to be a non-zero integer. It was 1, 2, 3, minus 1, minus 2, minus 3. Here, you're allowed to also have 0. N equals 0 is a bright fringe. They make, although I will not attempt to describe it, they make a device that's called a diffraction grading, which is essentially a whole lot of these slits all ordered in a row. So instead of having 2, you have many. If you use a diffraction grating, you shine a laser through it, the resulting interference pattern gives you nice, evenly spaced bright spots on your screen. So it'd be equivalent to getting, say, a bright spot here, and then nothing, and then a bright spot here, and then nothing, and a bright spot here, and then nothing, and so on. And how far apart they are depends on how closely spaced these slits are, and it depends upon what wavelength your laser is, and it depends upon how far this is from your diffraction grading. Diffraction grading actually is one of the more useful devices we have out there. It's what you use to make spectrometers, among other things. What do spectrometers allow you to do? Well, they allow you to figure out what kind of gas is present in an object. So, for example, the astronomers love these because they can look at a star, they can use the spectrometer to tell them what gas is present in this star. Is it all hydrogen? Is it hydrogen and helium? Is it helium and carbon? Is it some mix, etc.? And from that they can figure out stuff like how old is the star, or how much of its fuel has it burned through, etc. How long until it burns itself out. If you shine white light through it, and this is what this picture is showing, then you get a rainbow on the outside, on the other side of it. There is one other topic of importance to this entire chapter. I'm going to scroll back to it because I skipped over it since it wasn't going to fit yesterday. And that is on the topic of polarization and vision. We talked a bit about polarization earlier, but I wanted to kind of go back to that a little bit because it's a little bit of a preview of what we're going to do in Chapter 8, which is electricity and magnetism. What happens is light and any other type of electromagnetic radiation is basically an oscillation of an electric field and of a magnetic field. So what are electric and magnetic fields? Electric fields basically are a thing that applies a force upon a charge that's in the same direction as the arrows are pointing, depending on the sign of the charge, of course. Magnetic fields apply forces on charges which are perpendicular to the direction in which the field is pointing. And also you have to have a moving charge for them to apply some force. So light consists of something like this. It's a changing electric field strength, it's a changing magnetic field strength. Polarization basically tells you what direction is the electric field in. And the way that polarizers work is they consist of very long chain hydrocarbons. Means you have some atom that maybe looks like this. There may be branches. This is sort of a simplification. And you have electric charges, electrons, which can be somewhere in this chain. Now, if the electric field is like this, then the electron will try to accelerate this way against it. And so it basically is able to move along the chain. And what that does is it absorbs some of the electric field. That's energy conservation. If it absorbs the electric field, that's equivalent to saying it absorbs some of the light. Now imagine that you have a bunch of these. Each one absorbs a little bit of light. A bunch of these together ends up absorbing a lot of light. And that's basically how your polarizing sunglasses work. If if the electric field is oriented in the same direction as the polarizer, then it gets absorbed. If, on the other hand, it's oriented this way, then there's not a whole lot of acceleration that the electron can do. There's not a whole lot of absorption possible. It turns out, though, that when light is reflected off of a surface, like water, for example, it tends to polarize it in a particular direction, predictably, reliably, every time. And so your polarizing sunglasses are designed to absorb the light that comes from that particular direction. For what it's worth, if you take off your polarizing sunglasses and tilt them like this and then look through them, you'll see that they don't actually absorb the light off of the water anymore. You'll now see glare off of the water. And I think on that note, we are done with this chapter and done with today.